now that we learned about the surface states of Weyl semimetals, we can ask something about phenomenology, something about the interesting phenomena that they might display. And in particular, in the case of Weyl semimetals, the most interesting effects arise when you expose them to external fields. This can be magnetic fields, this can be electric fields, and the most interesting situation is when you combine the two of these together. So let's start with a magnetic field. When you apply a magnetic field to an electronic system, you know what is going to happen to the band structure. The band structure is going to break into Landau levels. The Landau levels are very similar to those that you've already seen in the chapter for graphene, because they are Landau levels of a Dirac spectrum, of a spectrum that is linear in the momentum. But there is a very important difference from graphene, which is that we need to add the third direction. And this is the direction along the magnetic field, namely the translationally invariant direction. So in this case, the Landau level will be dispersive. They will not be flat. And here I'm showing the band structure. N is the Landau level index that you already know. LB is the magnetic length. And K is the momentum direction that is parallel to the direction of the magnetic field. And you can see a set of dispersing Landau levels, n equals 1, n equals 2, n equals 3, and so on. And there is also the symmetric counterpart on the bottom. But we may ask, what happens to the topological effects of the system? Where did the monopole charge go? And the answer is that for this particular system, all of the topological properties that were encapsulated in the monopole charge are now transferred into what is known as the zero Landau level. And this zero Landau level is this chiral mode here. Let me write down the dispersion of this. Okay, so C is the chirality, and K is the same momentum. So this dispersion is completely linear, and I want to point out something very important about it, which is that the magnitude of the magnetic field doesn't enter this expression. The magnetic field might determine the direction of the dispersion, but the magnitude of it is not important. Namely, if you introduce a very small magnetic field and the upper and lower Landau levels will be very much piled together, there will still exist this chiral mode propagating. And the consequences of that chiral mode are quite far-reaching, because we know that the group velocity of the electrons is defined by the derivative of the dispersion with respect to momentum up to some h bar. Okay? Therefore, you apply the magnetic field, there are no electric fields applied, and you get a chiral mode. Therefore, you have a finite velocity. And it doesn't matter where your chemical potential sits, there will be a bunch of states that will be moving in the direction of the field. So this is a current. A current is a response of a magnetic field. So what happened here? We have a chiral mode, and it gives us uncompensated current, and this is in total equilibrium. We didn't turn on an electric field. Okay? And the current is given by this expression. It's just the chemical potential times the magnetic field, and you can find this expression easily by considering the degeneracy of the Landau levels. This C here is the chirality of the node. You can flip the chirality of the Landau level by changing its sign. This is called the chiral magnetic effect. That's a very well-known phenomena, also from high energy. And here you can understand it quite simply from the Landau level picture. So how can we live with this? How can we live with a finite current that is generated as a function of magnetic field, just by the application of the magnetic field? That is not too complicated, because we remind ourselves that each Weyl point has to be accompanied by its partner with opposite chirality. And that partner will also have a chiral Landau level. And that chiral Landau level will also contribute the same number of chiral states if we are in equilibrium. So in fact, the chiral magnetic effect current, the total chiral magnetic effect, when we sum over all the contributions given by all the Weyl points, if the chemical potentials are the same, and this is a key factor, if all the chemical potentials are the same, then the total chiral magnetic effect current in equilibrium will be 0. So how can we see this? How can we extract a finite chiral magnetic effect? Well, the answer is we already gave it. Basically, we have to take the system out of equilibrium. And the way we are going to do this is by adding an electric field. Okay? If we add an electric field that has a component in the direction of the magnetic field, then something interesting is going to happen. Namely, there will be a chiral flow or a spectral flow of states near each of these Weyl points. But this flow will happen in the same direction. But given the fact that the lowest Landau level has a opposite dispersion, what we will find is that in the vicinity of one Weyl point, states tend to slide down along the Landau level, and near the vicinity of the second Landau level, second Weyl point, states tend to slide up. So this means that around one Fermi surface, states disappear, and around the other Fermi surface, states are accumulated. Okay? And if we were to consider only a single Weyl point, if we were sitting only in the vicinity of one Weyl point, it would appear as if charge is not conserved. And this effect has a name. It's called the chiral anomaly. The chiral anomaly is the non-conservation of chiral charge. This is exactly what we are observing here. And the chiral anomaly is indeed proportional to the scalar product of the electric field and the magnetic field. As long as they have two components that are parallel to one another, you will get a non-conservation of charge in the vicinity of a Weyl point. This is just the continuity equation, and this derivative is a 4 derivative. All of these are 4 vectors, so J contains also, in this case, a density contribution. Okay, so the chiral anomaly is the non-conservation of chiral charge, and in a band system, it's pretty easy to understand how to fix it. Basically, why does charge vanish from one point and how can it appear next to the other? And the reason is that the chiral Landau levels are actually connected via the bottom of the band. This is a lattice system, and therefore it is periodic. It will be also periodic from the outside, but the most important part is that the chiral Landau level actually gives us a channel that connects the two Weyl points to one another, allowing for this spectral flow. Okay, so now finally I want to discuss another unique property of Weyl semimetals that you can observe in experiment. You could also observe potentially the chiral anomaly in an experiment, because that gives a contribution to the current, and the contributions to the current are manifested in transport properties. Now we want to talk about another transport property, or another aspect of Weyl semimetals that might be reflected on transport properties, which is called quantum oscillations, or Weyl orbits, or bulk boundary orbits, or bulk boundary quantum oscillations. And this is a unique phenomenon to Weyl semimetals that really gives us access to the physics of the chiral Landau levels in the bulk, along with the physics of the open Fermi arcs at the surface. So what are these quantum oscillations? I want to remind you that quantum oscillations is a pretty common tool to study Fermi surfaces of electronic systems. You apply a magnetic field and the electrons start drifting due to the Lorentz force, and this is used many times to characterize the Fermi surface and give us quite accurate measurements of that. In a Weyl semimetal, there's something quite different that happens. Let's imagine that we apply a magnetic field that's perpendicular to one of the surfaces. So we already discussed the fact that this magnetic field generates chiral Landau levels in the bulk. So here I'm denoting the directionality of the motion of the particles. And I want to point out that this is a mixed momentum space and real space picture. Namely, this direction is the real space, it's a coordinate, but the two planar directions are momentum. Okay, so particles in the vicinity of some Weyl point around ky and kx point are going to move upwards, and particles belonging to the second Fermi surface that is around the second Weyl point will move downwards. It will look something like this. Okay, so this moves up and the other one moves down. And now you will ask yourself, what happens when they hit the surface? And what will happen is that they will hit the surface in the vicinity of the projections of the points. Namely, when they hit the surface, they will directly link to the arc. So they get here, and I remind you that in order to move downwards, they have to switch chiralities. Okay? The chiral Landau level with the opposite direction exists near the other Weyl point. So they have to somehow transfer between chiralities, and this is a process that happens quite naturally due to the Lorentz force. The Lorentz force happens because the magnetic field is perpendicular to the surface, and therefore it causes the particles to slide along the Fermi arc. I remind you that each point along the Fermi arc has a different kz. In this case I denoted it by ky, has a different ky value, and therefore they will switch ky values until they reach the other point. So it will look something like this. This is a motion in momentum space. The two-dimensional space is momentum space. Then they've reached the projection of the other Weyl point. What will they do then? They will sink into the bulk, because I remind you that the Weyl point is the point where the bulk gap goes to 0. So there it is allowed for the particles to connect to the bulk states, and this is a way for the particle to move all the way to the bottom surface, where again it is subjected to the Lorentz force, and it can trace that trajectory back along the other arc and get back to its original position. So this is a closed contour that involves motion along the chiral bulk channels and also along the Fermi arc. And you can calculate the semi-classical quantization condition This will give you quantized levels. And these quantized levels will be manifested in density of states that you can measure, and then we'll also enter in quantum oscillations as a function of magnetic field, because if there is a finite surface or finite Fermi surface that is encapsulated by the two arcs together, of course one on the top surface and one on the bottom, then there will also be a trapped flux. So there is a dependence on the magnetic field coming from this fraction of the trajectory. Okay, so what will this look like in real space? In real space, I told you that the trajectories of the particles on the surface are chiral and perpendicular to the arc. So now I'm plotting all three space dimensions. The motion in the bulk you already know, and the motion on the surface now is just in real space, because there is a chiral channel that takes it for some time until it finishes moving along the arc and then sinking. From this real space picture, it's actually rather easy to realize that sometimes this trajectory will be completely parallel to the magnetic field. So to summarize, I told you that Weyl semimetals in a magnetic field host dispersive bulk Landau levels. The lowest, or zero Landau level, is chiral, and it encapsulates the entire topological properties of the system. The dispersion of the lowest Landau level is field independent, and each Weyl point contributes a finite chiral magnetic effect current as a response to the application of the magnetic field. Together in equilibrium, all the Weyl points will contribute no net chiral magnetic effect. But if you switch on an electric field and you take the system out of equilibrium by pumping charges between the Weyl pockets, you can observe this finite current, and this is called the chiral anomaly. And finally, we also mentioned that Weyl semimetals in the presence of a magnetic field can show a unique type of quantum oscillations called bulk boundary quantum oscillations. And these require motion both along the chiral levels in the bulk and a spectral flow along the Fermi arcs.